And apart from that, I should understand how the hypothesis testing is set up, and how the strength of the hypothesis testing is evaluated. Okay, and on which a mathematical model I can see the strength of the hypothesis, and whether should I consider my null hypothesis, or whether I should reject my null hypothesis. It Everything we are going to take on in this class, right? So what I've done is I have taken a simple example. So I set up an example of hypothesis testing between uh, the girls salaries and boys salaries who joined Infosys on 2011, and I'm trying to compare their salaries on 2018, having said that uh, though they joined on 2011 from the same base, uh, but there could be a possible of these salaries are differing from each group. Okay, here my group is categorical variable gender, say male and female, and my continuous variable on the response side is their salaries. So my default assumption is their salaries are same irrespective of their gender. Now I need to set up a hypothesis testing. So what sort of hypothesis testing I will set up? I will set up ANOVA in this case, right? So my what I have done, how this will be evaluated mathematically, that's what we are going to understand here. Okay, what I have done is in my x-axis, I have taken the continuous variable, nothing but my salary, right? And in my y-axis, I have taken the frequency, right? Right. And then when I plot the data of individual salaries against the frequency of the gender, I say I found male and female. Now I got a one distribution for male and another distribution for female. Okay, so let's say this is male distribution or boys, and this I got it for girls, right? This I got for girls. Yeah. So in this case, my assumption is boy salaries and girl salaries are same. So this is what? So how I can get the boy salaries? I can say the boy salaries are represented by their mu. I mean mean salary, isn't it? So I can get mu1. Similarly, I'll get the salaries mean salary of girls as mu2. Now, how I will prove statistically the boy salaries are far different from the girl salary. So by picture, I can say it looks different, but I need to prove statistically, right? So if there is a too much of overlapping, it is very difficult to decide whether the boy salary and girl salaries are same or not same, right? So how this is evaluated, how the strength of the difference is evaluated, this is what we are going to understand, right? Now, what I'm trying to find out here is, so boy salaries and girl salaries all together coming from one population, isn't it? The population is salary, isn't it? So let's, so how it will be? Let's do one thing. So it will be here. So I can have here, it will be my gender, right? And this will be my salary, right? So my data will be here, boy Okay, so I can say male. Okay, the salary will be 25,000, something like that. Female. Okay, so it will be dot 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 dot, right? This is what the population in gender is one population here, and salary is another population. So the entire population variation. So and the entire population mean. What I say is that is a grand mean. So grand mean of or grand mean or the mean of your salary population is nothing but what I can say mean of my boys plus mean of my girls together. You can sum them up and divide by 2. That will become my grand mean, right? Can I say like this? The mu will be right mu1 plus mu2 divided by 2. Yes, yes, right.
Yeah.
So here let's try to find out the total variation in my population. Total variation in the sense, what is variation? Let's understand these concepts. This is called grand mean, okay, right? And now I'm bringing another keyword, total variation. So what is total variation? Can somebody say? We have understood standard deviation, variance, variation. What is total variation?
The sum of all variances.
Sum of all
Variances.
variance, variances. Karthik,
From the grand mean.
from the grand mean. Karthik. Hmm. Okay. So yeah, you guys are partially correct. So the variation is talking about your. Yeah, if you say the variance, that makes sense. Total variation is nothing but each individual data point, sum of variance of each individual data. Yeah, Karthik, that's correct. So the sum of variations, sum of variance of each individual data point is nothing but total variation. Okay, so in my boys, I will be having x1, x2, x3, x4, isn't it? Say is data
Yes.
point, right? Say x1, x2, uh, x3. Okay. Let's say I have n1, n1 records. Fine.
Yeah.
And here, girls, I have y1, y2, y3. Okay. Isn't it? So all these data points. And here, girls have n2 records. So what will be my total variation? Total variation will be
X1 minus grand
yeah.
mean.
So I is equal to 1 to n 1, yes, x I minus
Grand mean.
mu, right,
Yeah.
right,
Yes.
from grand, yeah. And then the second will be I
I
1 to
N I
n 2 yi
minus
minus,
mu the whole square.
correct, isn't it?
Yes.
Right.
Yeah.
So this is what my total variation. Okay, we understood what is total variation. Now, this is what it is talking about. See, if you see this, I have taken you through one, um, yeah, here, total variation in my population. So now sum of squares of variation in my population. So I have covered this, what is SSY. Okay, so this is also told as SSY. So I can put it like this, right? Total variation SS, and I'll say Y. I got it. Now, this total variation SSY, what I can say is the variation within each group. When I say each group, in the sense within boys distribution, okay, plus,
Mm-hmm.
and total variation within girls group, within girls distribution, plus the variation of mean or the difference of mean of boys to my grand mean, and the difference of girls mean to boys mean. So what I'm trying to say is, suppose I want to find out the total variation of boys, okay, is nothing but this is what total variation of boys, isn't it? If I say this is what my total variation of boys, this is what total variation of girls. Now this one I want to represent in another way, that is the total variation within the group plus the variation from mean of the group to grand mean. Can I
Yeah.
say that?
Yeah.
How I can represent? Let me do that. Let me do that, because this is what you guys need to understand, and let's take little more time and clarify it. Now let's say the all boys and all girls are collapsed to their mean. Okay, all boys and all girls are collapsed to their means. What it means? So what I'm going to do here, let me put that. Okay, so now let's say all boys I have collapsed all n points, n1 points, isn't it? All n1 points are collapsed to their mean only. Okay, all n2 points collapse to their mean only. Okay, so how many points are collapsed here? N1 points, isn't it? Now how
Yeah.
many collapse here?
And two.
N2 points, right? And what is my grand mean?
Yeah.
Mu, right? So what is the difference between your mean? So what is this one? This is M1,
M1. Yeah.
right? And this is M2.
M2.
So what is the difference between the group? The difference between the group is nothing but the difference between mu1 of the group to mu2, sorry, grand mean, plus mu2 to mu1, sorry, mu2 to mu. I mean, what I am trying to say is, so let's see, what it have is two things it have. So sum of square between the groups and sum of square within the groups, right? Now sum of square between the groups means, what it is saying is the this is the variation in y related to the variation in the means of the categories of x. This represents a variation between the categories of x or the portions of the sum of squares in y related to x. So what it is saying is, now you collapse all the data points of boys and all the data points to girls to represent their mean itself. So now all n1 points of boys, let's they collapse to their mean value. Now how many points I got? N1 points, and I all say there are mu1, and here I got n2. Now what I'm going to do is the sum of square between the groups is nothing but n1. How many I have? N1 of mu1 minus mu whole square, isn't it? So for each individual data point, the difference is mu1 minus mu whole square. How many points I have? N1 points, right? Now in this case, how many I have? N2 mu2 minus mu square, right? This is nothing but my between the group difference. So between the group difference means I have group 1 for boys, I have group 2 for girls, and now boys group mean to grand mean, girls group to grand mean is nothing but the difference between the group, right? Is it clear? Is it clear why n1 multiplied with mu1 minus mu square plus n2 mu2 minus mu square is a difference between the group, sum of squares of difference between the groups? Aril, Vinod,
Yeah, I got it, Lakshmi.
right? So
Yeah,
this is
correct.
so then there is one more thing is, now what is the sum of square within the group? Within the group means
Within the
can
boys group specifically.
so what will be the value in this case?
N1 minus N2 minus N3.
Why n1 minus n2 and
Oh, sorry.
within the
Yeah, not N1. I mean the observations within N.
ha
Sigma x pi by n.
ha so this this area is called, this is what this is your
Within the group.
sum of square,
Between the group.
yeah, between the group xy. Okay, I think this is what they have say xy, right? So this is what between the group, sum of square between the group. Then there is another one thing is within the group. Within the group means what it will be, sum of square within the group, sum of square, and we say always as a error. This is as always as a error. This one is talking about, yes, I is equal to 1 to n1. Okay,
Mm-hmm.
it will be xi, huh, mu1 square, mu1 square, please understand, and the other one will be I is equal to 1 to n2, okay, yi minus,
Minus mu2.
yeah, okay. So this is called sum of square within the group. Now why did I say sum of square within the group as error? Let's try to find out what is why it is called error within the group and why it is called sum of square between the group as ss square xy. Now we understand that the total variation is xi minus mu square. I mean I is equal to 1 to n xi minus mu the square plus I is equal to 1 to n to y1 minus mu whole square. See, if you see the total variation is nothing but, now I can say my SSY is nothing but sum of square, okay, sum of square between the group, okay, plus sum of square within the group. Is it true or not? Sum of square total variance in the data set is nothing but the sum of square, or sum of square within the population is nothing but sum of square between the group plus sum of square within the group. Is there any confusion to anyone else in this case?
No.
No? Correct. Good. So now, which component represents the no I mean strength of two groups are different from each other? Which component? I got SSY, which talks about the strength of the difference between sum of squares of means, right? So, or sum of squares of group means, isn't it?
Mm-hmm.
And
Yeah.
the other one is talking about sum of square of your individual group differences or individual group variation. So,
Mm-hmm.
in entire SSY, if it in SSY is 100, okay, the total difference is 100, right? In my 100, SSXY is 90, okay, and SSY error is 10. So what it represents?
That SSY is more correct, maybe.
In the total variation, it tells that 90% of the variation is coming from difference because the means are differ from each other. Okay, only 10% of the variation coming from the variation within the group. Okay, it means that these two groups are far from each other. They are completely distinguishable, right? The,
Yeah.
the difference between the groups is highly significant in the variation, in the data variation, right? So this is what we need. If the groups can be distinguishable with more prominently, then I can say, yeah, these groups are different from each other, right? Isn't it? If I cannot distinguish them because of lots of overlapping, okay, or because of uh, um, so much of flatness of the data, then it is not possible to judge that both the groups are different from each other. Okay, I can say these groups are different from each other if their means are far away from each other and they have a less interference, less overlapping, right? Isn't
Mm-hmm.
it? And this will come from your sum square of um, uh, some square of error and some square of within the group, some square of no, some square of between the group. Okay, the sum square of between the group gives us confidence about the groups are differ from each other. Sum square of no error, which is nothing but sum square within the group, tells us the groups are not much differ from each other. So in the total variation, you have to find out which component is prominent. If your sum square of error is prominent, then you have to reject the null I mean you have to stay with the null hypothesis and say both the groups are similar to each other. Okay, But if in your hypothesis testing you found some square of between the group is more prominent, then you have to tell the groups are different from each other. Okay, so how we are going to do that? Let's so the entire mathematics, the math, what we have found here, what they are doing is, now you divide SSY by, okay, yeah, hmm. So it will be 1 plus SS square by error by SSY. Let me confirm it. I just wanted to, this is this the one eta square they are talking about? Eta square, yeah, this is what we have studied, isn't it? Total sum square of sum of squares is nothing but sum of squares between the group and plus sum of square within the group. And what they are saying, so SSY is equal to SSX plus SS error. Now SSY is total variation, SSX is nothing but sum square of um, you know um, uh, some square of within the group, I mean n yj minus y all the square, and SSY is nothing but within the group variation, right? So this all fine, and then this is what they have done, trace all these values between the group and within the group, and the measure of effect is SSX divided by SSY. Yeah, this is what I have made a mistake. Yeah, so what they are telling is, now what I can say, SS, okay, what it's saying, SSY minus yeah, SSY minus SS error is equal to sum square of SSXY, right? Now, so what they are telling, and this is what my eta square, SSX by SSY is equal to, SSX is what? SSX is within the group, okay? And SSY is the entire variation. Now SSX by SSY is nothing but SSY minus SS error divided by SSY. Okay, so here they are telling is SS, and you divide it with SSY. So now tell me, what will be the range of value of SSX divided by SSY? What will be the range of this value? What will be the range of this value? Hmm? Yeah, Karthik had told us it will be 0 to 1. Why it will be 0 to 1? When it will be 1? Tell me. When it will be 1? Yes. When your SSY is 0. Isn't it?
Okay.
Isn't it? Sum square of error will is a 0. So when sum square of error is 0, it means all the values of boys are on the same line, and all the values of
Mm-hmm.
girls on the same line and the same value,
Mm-hmm.
isn't it? What is sum
Yeah.
square of error? Sum square of error is nothing but sum
Difference
square of
between each data point. Sum of difference
from
between each data point
each data point from their group means,
from their group mean.
isn't it?
Yeah.
Right.
Yeah.
So all the data points when they sit on the group means, so there is no difference. So it will become zero, right?
Yeah.
So that time you will be finding both the groups can be easily distinguishable,
Mm-hmm.
right? And you can
Yeah.
easily predict whether they are same or different. Right, look at the component who is playing a critical role. So if you find the variation within the group is very large, it creates a lot of problem to predict or estimate whether the groups will be different from each other. So the variation within the data set plays a critical role when you try to take a business decision. Okay, mean is one of the part, as, as well as mean, the variation also plays a critical role. So this variation is generating SSE. So if you have a larger SSE, okay, larger SSE, then 1 minus, okay, SSE. So now let's say in this case, this is constant, isn't it? SSY square plus SSXY square plus SS error, this is constant, isn't it? Now, if your SS square error is very large, then SS square XY will be small. So at that time, you will be finding SSY is nothing but SS error, right? So when SSY is equal to SSY, so division of this will give you 1. So 1 minus 1 is 0, right? So it says that when this value tend to 0, it means that the strength of the difference is very negligible, and you cannot say whether these groups are different or whether these groups are same. Got it? When your sum square of error is very small, then you will be able to tell that these groups are different significantly. So based on the value of, you know, this eta square, okay, this SSXY by SSY is nothing but we say as eta square, and based on the value of eta square, I can say these groups are different from each other or these groups are same to each other. Okay, now the value ranges from 0 to 1. Okay, it will become 1 when your SSA is very small. SSA will be small when all your data points are nothing but they are the same as your group mean,
Group
right?
mean.
Yeah.
Yeah.
Or if your distribution is very narrow, right? In that case, or you can say the cortices value is too high, then you will find the data is more towards your mean, and you will be finding in that case you will be finding that it is easy to predict whether the groups are same or not, right? Something like this, suppose. Okay, if you have some group like this, it's easy to predict, isn't it? Now
Yeah.
suppose if you find some group like this,
काय झालं का?
you cannot predict whether they are same or not, or it will be difficult, but that you can only judge based on the eta square value. If your eta square value is near to 1, it says that the strength of difference is significant, and if the eta square value is close to 0, it says the strength of a difference between the groups is insignificant, right? So like eta square, there is another variable called f test. Let me also take you through the f test. Okay, so f test also will give us some insights, and I can use that to find out whether I can reject null hypothesis or I can accept my null hypothesis. Okay, guys, tell me, so for which value of eta I will stick to my null hypothesis?
Lakshmi, could you repeat the question, please?
So for which value of eta square I will accept my null hypothesis? Okay, Karthik have told one.
Not sure, Lakshmi.
So when I will accept my null hypothesis, what is my null hypothesis?
That there's no variation, what are the groups almost similar.
Okay, so on which eta value I say groups are same?
1.
1.
When it is towards 1, because 0 means there is difference and 1 is almost harder to distinguish between them, right?
Is it? So when you will get 1?
When the groups are different.
When the groups are different, is it? When you
Yeah.
will get 1? So no, when to get 1, you will be finding the SSE is small,
Mm-hmm.
right? Now SSE
Mm-hmm.
is small means you got 1. It means the groups are quite differentiable,
Mm-hmm.
right? So if the groups are quite differentiable, then what I should do with my null hypothesis?
You
You
should
should
reject it
reject
then.
the null hypothesis.
Yes, you have to reject the null hypothesis, isn't it?
Yeah.
And when you get 0, the eta square value is 0, what I should do that?
Accept the analysis.
Accept the null hypothesis. Is it clear?
Yeah.
We know,
Direction.
clear, right?
Yeah. Yeah.
Yeah. So this is how the eta square value will be evaluated from your model. Okay. When you are going to run a model, what you will be finding is you will run the model and it is going to give you only eta square. It will tell you, okay, eta square value is 0.02. Okay. Eta square value is 0.98. So based on that value, you have to decide whether the model is telling to accept your null hypothesis or to reject your null hypothesis. Got it?
Yeah.
Like just the way the p-value are thrown from your statistical testing, right? So when your p-value is less than 0.05, what do you do? P-value less than 0.05.
You
Accept null hypothesis.
reject.
Accept or reject?
If it's less than
Re-
0.5, you reject it.
Uh-huh. We're not clear?
Yeah. Yeah.
Yeah, so like the way the p-value, you just look at the p-value of any other z-test and t-test, you have to check the eta square value from the ANOVA model point of view. Okay, if eta square value is equal to 1 or nearly equal to 1, then reject your null hypothesis. If it is 0, then accept your null hypothesis. That's it. That's what your hypothesis test or the ANOVA test model is working. Okay, so definitely this is how the ANOVA model will work. But to set up the ANOVA model or to set up the ANOVA test, what you need to do is you have to ensure that the data what you have taken follows a normal distribution. So what we have is there are a set of assumptions which should be satisfied before you set up the ANOVA hypothesis testing. Okay, now we have to ensure that when we get the data, we need to clean the data and we need to prepare it. Once the preparation of the data is done, what we need to do is we have to ensure all our assumptions are satisfied by the data set. Okay, if any of the assumptions are violated, then the model results cannot be taken for any business solution, or you cannot take the model result as they are accurate, because underlying assumptions are all limitations of your mathematical model what you have taken. See, all statistics is coming from your inferential statistics. Inferential statistics is talking about your central limit theorem talking about your random sampling, isn't it? Your normal distribution, all those assumptions are already laid out. If any deviation there in the data set, then underlying assumptions will not hold good, and ultimately it will give us erroneous result. Okay, so ensure that you satisfy the no, assumptions. Uh, if they are satisfied, then you can go ahead and set up the hypothesis testing. Okay, we'll look into it, how how and what kind of assumptions we are going to satisfy. Okay, so this concept is clear, all clear,
Yes.
everybody? Yeah.
Yeah.
Okay, great. Okay, this is what I have told. Okay, this I have shown it. Okay.